If you have a top-loading washing machine, you may have opened up the lid while the clothes are in the spin cycle. Usually when you do that, there's a safety feature that as soon as you lift the lid, it turns off a switch and it kills the motor and it stops spinning around, right? But this thing spins at a really high speed, and if you can find where that safety mechanism is, you can often jam your finger or a pencil or something in there and keep it spinning around. And the side view of it would look like this. Here's a clump of wet clothes stuck to the side of the washing machine, and the washing machine is spinning very rapidly in this direction. So there must be a centripetal force pushing on your clothes, right? And there is. It's normal force. The side wall is pushing inward on your clothes, and that's why the clothes go in a circle. So in this case, we say the centripetal force is provided by normal force. The top view looks kind of the same. There's the clump of wet clothes. There are all these holes in the drum of the washing machine. So what happens is all the water droplets, all the moisture in your clothes, if this is spinning around in a counterclockwise direction, the clothes and all the water want to follow the law of inertia and travel in a straight line. Because there are holes in a lot of places, well, wherever there's a hole, then that portion cannot provide a normal force. So the water droplets have a tangential velocity, and they don't fly out, right? Out would be this way. So it's not that the water droplets have a centrifugal force acting on them. Rather, they follow the law of inertia because they lack a centripetal force. But the clothes do have a centripetal force provided by the normal force, and so the clothes are able to go around in a circular path while the water flies off tangentially. I've been on a ride at an amusement park before in which you play the role of the clothes, and here's a picture of it, and you can see all these people's feet are well above the floor. So the ride starts out like this. You get in and you stand on the floor inside of what's basically a giant version of like a washing machine, and then the whole thing starts to spin around with some speed, and then this floor drops down once you get up to high enough speed, and so you end up like these people who seem to be stuck high up on the wall. Well, the reason they stay there is because there's some coefficient of friction. So if we make a free body diagram for this person, there's a normal force pushing them inward toward the center of the circle. There's a pull of gravity, but they don't fall downward, right? How come? Because there's a frictional force this way. Remember, frictional force is greater than or equal to mu static times the normal force. So let's say this person has a mass of 60 kilograms, and the radius of this ride, we'll say it's about 15 meters. Okay, then what's the angular speed? So remember, there's two ways to describe how fast things move when they go in circular paths. You can give the number of meters per second, that's v, or you can give the number of radians per second. And that's not a w, that's the Greek letter omega, right? And the way it works out is we can always get the linear speed in meters per second by multiplying the angular speed in radians per second times the radius. Okay, so we know that centripetal acceleration is v squared over r. So if we make a substitution, that means it's omega times r quantity squared over r, which gives us omega squared times r. So the question is, what minimum value of angular speed in radians per second is required for this person to be stuck to the wall? Oh, and let's say that the coefficient of static friction is 0.9. Often on rides like this, the walls are lined with carpet to increase the coefficient of friction. Okay, so based on this free body diagram, the force of friction has to at least be equal to mg. So force of friction is equal to mg. So in the limiting case, mu static times normal force is equal to mg. But because those forces have canceled each other out, you're left with normal force as the unbalanced force. So the unbalanced force, or the net force, is the normal force. That means ma is normal force. And in this case, the acceleration is centripetal. So we would often say it's mv squared over r is normal force. But because we're asked about angular speed, not linear speed, we'll say m, and then instead of substituting v squared over r for centripetal force, we'll substitute omega squared times r. M omega squared times r is normal force, so we make that substitution here. And the coefficient of static friction times m omega squared r has to equal mg. Mass cancels out, so as long as any one person is stuck to the wall, everyone will be stuck to the wall. Well, that's provided that they're all wearing clothes made out of similar fabrics, so the coefficient of static friction is the same for everybody. Okay, so if we rearrange the equation, omega squared is equal to g divided by mu times r. So omega is the square root of g divided by mu times r. So in this case, it's the square root of 9.8 meters per second squared divided by 0.9 times 15 meters. Grab a calculator, see what we get. And omega comes out to about 0.85 radians per second. So that's pretty fast. Remember, on the unit circle, a radian is about 57 degrees. About here. So if you were going 1 radian per second, you'd be going 57 degrees per second. If you go 0.85, that's about 49 degrees per second. So that means it takes about 7.4 seconds to spin all the way around one complete circle. Okay. The same concept is used to simulate gravity. If we're going to send any manned missions to Mars, it's going to take several months to get from Earth to Mars, and to travel in a zero gravity environment for that long would be, it would have devastating effects on our physiology. So it would be nice to not have our leg muscles atrophy, and to be able to digest and process food without all the complications of a zero-G environment. And the list goes on why we would want to have a sensation of feeling an acceleration due to gravity of 9.8 meters per second squared on that journey. So one way to do it is to create some sort of spacecraft in which the object continuously rotates. So if we simplify this diagram like this and zoom in, then the whole idea is that you're standing with your feet against the outer wall of this cylinder, and then a normal force pushes you toward the center of the circle, right? Normal force is providing the centripetal force, and we want that normal force to feel exactly the same as your weight would feel, right? If we rotate this diagram 90 degrees, then it just looks like somebody's standing on the ground. And when we stand on the ground, our normal force pointing up perfectly balances mg. Of course, when you stand on the wall of this space station, there is no pull of gravity, but there is a normal force, and we want it to feel just as large as the gravity we would feel on Earth. But we see that that normal force is the only force acting on this person as this spacecraft spins around. So the net force is equal to normal force. The net force is mass times acceleration. In this case, the acceleration is centripetal, and the normal force should simulate the field of gravity. So mass cancels out, and the centripetal force should be just as great as 9.8 meters per second squared. This means that v squared over r is equal to g. So if this space station had a radius of, let's say it's really big, right? Like a full football field, so about 100 meters in radius, then how fast would somebody standing on the inner wall, what would their tangential velocity be? Rearrange this equation, and the velocity is the square root of rg. So in this case, their tangential velocity would be the square root of 100 meters times 9.8 meters per second squared, or in other words, the square root of 980, which would be about 31 meters per second. Okay, well, thanks for watching.